Hello, everyone. Thank you for coming. I'm Christopher Rogers, and I'm a software engineer working online for iOS. As you can see here, over the history of Line, the amount of code in our iOS code base has been growing at a steady pace. Starting from 1.0 up until recently at 9.18, the code base has grown from 30,000 to about 1.4 million lines of code. With that comes many challenges from an engineering perspective, as you can imagine. Today, I'd like to focus on a few of the problems we've had building all of this code and how we've been addressing them. For the most part, I'll be describing build problems as they occurred in order to build up background knowledge for later topics. So let's get started. The first problem area I'd like to talk about is dependencies. By this, I don't just mean open source libraries you depend on. So any libraries you depend on. Adding them manually in Xcode works, but won't scale. Once you reach a critical number of dependencies, they become difficult to manage. I'm sure most of you are familiar with this. A header and linker search paths, linker flags like the C++ standard library you'd like to use. These are things that have to be configured with your build system. And then when you need to update a library, you have to make sure that the new version is compatible with the other libraries, and perhaps update some build settings. Later on, you may look at the build settings and find yourself thinking, what was this linker flag for again? Do we still need this search path? Again, I'm sure you're all familiar with this, whether you have a small or large code base. To address this problem, we adopted CocoaPods. We first added CocoaPods in 3.4 at the end of 2012. This was all it had back then. It integrates well with Xcode, as I'm sure you are all aware. But sometimes the default behavior wasn't what we wanted. So we had to add Ruby scripts to the pod file to modify the default configuration. For example, we wanted to override the iOS deployment target to be the same version as the one we set for ourselves. So that was something we had to figure out how to do. Nevertheless, CocoaPods was a tool that carried its weight. Then came along Swift. We had been using Swift since version 1.0 in 2014, but we had managed to get by 3 years without having to add any Swift dependencies. When we had to add a Swift dependency, we decided to add Carthage alongside CocoaPods. Carthage is another well-known dependency manager, so I won't get into too much detail about it. It pre-builds frameworks, so there's very little integration within Xcode. We were very reluctant to adopt another dependency manager. What if a Swift dependency wants to depend on an Objective-C dependency that we had added to CocoaPods already? That was our main concern. But we needed to release a new feature with a new dependency, so we had to adopt Carthage, basically. But to be honest, we had more problems with Carthage than we had with CocoaPods. They were mostly related to Carthage's caches. We had to write scripts to always prefetch code instead of letting Carthage handle it as part of its own bootstrapping. We also had a script to have it retry building a few times because sometimes Carthage would crash halfway through. However, there was some good news. We were able to eventually hook it up with Rome, another open source tool, to cache Carthage's build artifacts on a local server. This way, when someone updated and built something in Carthage, no one else had to rebuild it. However, we found that the remote cache would sometimes be poisoned, so we couldn't use it for QA testing and release builds. Next, I'd like to talk about how the app's launch time was affected. Since this presentation is focused on build problems, I'd like to mention one major cause of longer launch times that relates to building. That's dynamic frameworks. Adopting Carthage caused us to eventually have many dynamic frameworks. Upon app launch, DYLD will dynamically link your framework to the app. This doesn't come for free. The Instruments app, as of Xcode 11, has great tooling to help you measure how this impacts your launch time. So our solution to this was very simple. We just made them all static frameworks. This eliminates the dynamic linking part of the launch process altogether. However, there are a few downsides. You can't bundle resources inside of a static framework. You could, but static frameworks aren't needed at runtime, so they shouldn't be bundled. Also, if you have any app extensions, like a share extension, importing any static frameworks will result in your total binary size increasing compared to using dynamic frameworks. At the time, switching to static frameworks wasn't as straightforward as it might sound. Static frameworks weren't originally supported in Swift, and configuring Xcode to get it to build was a chore. That's no longer the case, thankfully. I'd like to take a moment to show you how to configure Xcode to build a static framework. First, start off by creating a dynamic framework target if you don't have one already. Next, open up the target's build settings and change the mock-O type from dynamic library to static library. That's pretty much it. There are some caveats, though. Like I just mentioned, you'll want to make sure the framework does not get embedded in the app. If you had any embedded resources, you'll have to create a resource bundle target for those and embed that instead. If you want to create a mixed target where the framework contains both Swift and Objective-C code, there are some things to keep in mind. Framework targets cannot have bridging headers like an app target can. However, if a framework has a Clang module counterpart, Swift will let you access that implicitly. Being a Clang module also has the benefit of being easy to use from Swift without having to modify your app's bridging header. Frameworks created in newer versions of Xcode come configured out of the box as Clang modules, so little is needed to be done. If you have an older framework target that's not a Clang module, you'll need to configure these build settings. By default, Frameworks come with an umbrella header, which, by convention, is a header of the same name as the framework that imports all of the framework's public headers. Xcode will also generate a module map for you that will use the contents of the umbrella header to define the module. So anytime you want to bridge something to Swift, you'll first have to make it a public part of your framework. This can be done in two ways. One is adding the header to the public section of the header's build phase. The other is to open the header file in an editor and show the file inspector in the right-hand pane. From there, you check the framework target in the target membership section and change the project setting to public. That's all you have to do, but if you want to customize more, you can by writing your own module map. That can be done by configuring the module map file build setting. Module maps have the module map file extension. I recommend using the module name as the file name instead of the typical module, as Xcode may auto-detect the module when you don't want it to. This is the basic template you'll need for framework modules, and is close to what Xcode generates for you. There are two customizations that I make from the default. The first is to remove the umbrella header altogether. Newer versions of Clang support umbrella directories, which you can use by just removing the keyword header. For frameworks, all public headers get put in the headers directory, so setting the directory name to headers makes all public headers automatically accessible as part of the Clang module for free. No more adding imports to the umbrella header, and no more umbrella header warnings when you forget to add an import statement to it. The second thing I do is remove the export settings. The export keyword allows you to specify other modules that will implicitly be available, just like includes or imports worked with textual imports before Clang modules existed. For example, importing UIKit lets you use foundation classes without having to explicitly import foundation. That's controlled by the export setting. I found that having modules implicitly imported makes it harder to move code between modules. Even for pure Swift modules, leaving the default umbrella header around will cause UIKit to be implicitly imported in all Swift files, since the umbrella header template contains a UIKit import. In this case, I would just delete the umbrella header. Getting back on track here, after converting most of our dynamic frameworks to static, we achieved an average 1.6 second improvement in launch time. If it makes sense for your needs, I highly recommend static frameworks. Next, I'd like to talk about bridging Objective-C and Swift. In particular, two problems that came up for us. For one reason or another, you may find yourself wanting to define an Objective-C category on a Swift class. If the category is being bridged back to Swift, you'll quickly find out that you can't for a couple of reasons. If you try this way with a forward declaration, you'll get an error saying you need the definition of the class. So we change it to import the file it's defined in, which is the generated header. This doesn't work either. The reason is that there would be a circular dependency between the generated header and the bridging header. The generated header imports the bridging header, but you need to import the generated header in the bridging header in order to declare a category on the Swift class. In another problematic situation, in our codebase, there are instances of Swift classes with custom Objective-C names that cannot be used in the bridging header. The methods these types are used in won't be visible from Swift, since we're only referring to the Objective-C name, class name with a forward declaration. There used to be many instances of this in our codebase, but Swift has been getting better at dealing with this. And now we only have one such problematic class. I also have developed a unique workaround to handle both of these cases that I'd like to share with you. But before I do, I'd like to mention that I seem to have fixed the second issue here. I recently fixed a simple bug in Swift for fun in my free time, which seems to have fixed this issue as well. Hopefully it will be included in Swift 5.2. But until then, my workaround is to create a module map for these problematic classes. Let me show you how to set it up. First, create the module map file. Its contents should resemble this. You just need to import one header file. The contents of the file should be what Swift generates in its generated header for the classes that we're interested in. We don't need the entire file, so in this file, you should just put the macros that are at the beginning along with the bare class interface syntax without any of its methods or properties. This is just for the Swift compiler to be able to map the Objective-C name back to its name in Swift. Then, place both the module map and header file in a directory that you can add as an include path for Swift. This is how it's set up for line. So, revisiting our header file, this is what it looks like when you import. When the Swift compiler is pre-processing this header, this double underscore Swift double underscore macro will be defined. So in that case, we import the module that we just defined. This lets us import the class declaration and thus declare a category on it. I created an internal tool to generate the header file from a definition file like this, so that the module header will always stay in sync with your Swift codebase. It extracts the type declarations using a tool called Swift syntax for the types specified and passes them to the Swift compiler with the flags appropriate for generating the header file. I'd like to open source it if there's any interest in it, so let me know afterwards. The next problem we faced that I'd like to briefly talk about is the size of our project, Xcode project. As our Xcode project file grew, we ran into a few problems. Regardless of size, everyone knows the pain of having to resolve conflicts in the Xcode project file. In order to properly resolve these, you have to understand how to read the project file to begin with. It mostly reads like a machine-generated file with UUID-like identifiers everywhere. It has many lists, but some lists need to be sorted while others don't. Since the file is machine-generated, it's difficult to understand where a given setting came from. Was this a default setting that was part of the target template? Maybe someone set it on accident. Maybe it was for some library that we no longer use. And with a project file size in the megabytes, modifying any part of the project in Xcode was painfully slow. So we eventually decided to adopt a tool called Xcode Gen. Project settings are written in YAML, which allows us to write comments to document settings when necessary. Since the source of most conflicts were adding and removing files, those conflicts have, for the most part, disappeared. In Xcode Gen, you specify which files and directories to include and exclude. So just regenerating the project will keep the project in sync. And there are now only a little over 1,000 lines of YAML to have to deal with. And this is probably more than most projects would have. So I'm sure you'll find great results with Xcode Gen. One drawback to keep in mind is that you will no longer be able to use Xcode to edit the project directly. So things like updating to the latest recommended project settings won't work anymore because they will just be overwritten the next time you generate the project. Lastly, I'd like to talk about some problem areas we identified affecting build time. When the generated header gets modified, it causes almost all of our Objective-C code to be rebuilt. Also, there are some tooling problems. For example, sometimes Xcode will decide to rebuild everything when nothing much had changed. Also, incremental builds in Swift can sometimes be too coarse-grained, where it recompiles more than it really has to. And when developers run into trouble building their code after pulling the latest changes, they often will resort to cleaning. This blows away perfectly good build artifacts from targets that rarely change, the main culprit here being dependencies in CocoaPods. There were some improvements we could make with a short turnaround. In regards to changes to the generated header, we precompiled it. In other words, we imported it in our prefix header. I just said that modifying the file was practically a clean build because it's like rebuilding every file. Well, this guarantees that every file does in fact get rebuilt. For this reason, this is usually a bad idea. The general advice here is to only precompile headers that don't change often. However, our generated header is so large and is imported in so many files that it ends up in a build time win for us. So you may want to look into this if you're in a similar situation. Another change that we were able to make to improve our incremental build times in Swift was to limit access to certain Swift extensions. Doing so can drastically reduce the amount of files that gets rebuilt. What I mean by this is limiting the scope of their APIs with access modifiers like private and file private, and moving extensions to their own files when necessary. The reasoning behind this is that when the Swift compiler determines what needs to be rebuilt, it considers changes to an extension as necessitating a rebuild of any files that could have seen the change to that type. In the current implementation of Swift, this means rebuilding any files that reference that type, and not just the methods or properties that were added in that extension. To make matters worse, when an extension is contained in a file that was modified, that extension is also considered modified, even if you didn't modify any part of it. So how do you find problematic extensions? There's a compiler flag here that you can add to other Swift flags that will dump logs from incremental compilation. By modifying commonly edited files and looking at the logs, you may find that more code gets recompiled than you may have thought. So take here, for example, this file. It contains code for my class and an extension on index set that adds the bar method. So whenever the file gets modified, the index set in its entirety gets marked as dirty. And if this type index set is widely used, it could be index set or even like UI view, for example. This will result in abysmal incremental builds. So how can we improve this? One easy way is to mark the bar method file private so that the compiler knows that it doesn't affect index set outside of this file. If bar is being used outside of this file as well, then what you can do instead is to move the extension to its own file. This way, changes to my class don't affect the extension on index set. In our code base, the problems that I observed often were due not to the file being marked dirty directly, but because of something depending on that file being marked dirty as a result. For more long-term improvements, the approach we're taking is to split up our code base into modules and to build and cache these modules using a tool called Bazel. This includes all of the dependencies managed by CocoaPods and Carthage. The approach we're taking to split our code base into modules is to first split modules into categories. A major motivation for this was that the dependency graph was starting to become too large for everyone to grasp. When adding new code, many people didn't know where to put it. Or when editing a smaller module, they wouldn't know what would be okay to import. There is also a consideration for reducing the binary size for app extensions. Since we're using static frameworks, importing a large module in an app extension will have consequences. For that, we created a category of modules that are the only modules safe to import from an app extension. But for now, we've decided to split some of our modules into a separate category, which we call feature private modules, or just feature modules. You could think of this as creating a package of modules. Feature modules have one restriction. They cannot import another feature's modules. Features may have multiple modules in which they can import each other. There are some other categories as well. Since they're not a part of any feature, they cannot import feature private modules. They should be small and focused to avoid bloat. When in doubt, create a new module. One thing to note is that some features may opt to create a feature public module in order to provide lightweight classes and protocols, for example. In order for this to work, we set naming conventions for our modules. In order to keep everyone aware of these new conventions while they code, I created a tool during our team hackathon last month to detect invalid imports. It looks something like this. Like the other tool I mentioned earlier, this one also uses Swift syntax. It parses all of the import statements and checks that they follow the rules we set based on our module naming convention. Here we get a message stating that the current module, which is part of the feature wallet, cannot import a module from another feature. So now that we know how to organize our modules, we need to actually build them with Bazel. If you're not familiar with Bazel, very briefly, Bazel is an open source build system created by Google. It's known for fast, reproducible builds. You don't need to clean in order to correctly build. It can also be configured to read and/or write build artifacts to and from a remote cache server. For some platforms, it even provides remote execution or parallel remote compilation in your build server farm. So our initial approach was to use Swift Package Manager, or Swift PM, for the dependency graph resolution for third-party dependencies, and to use the Swift PM target settings in package.swift to configure Bazel to build them as static frameworks. Bazel is not a dependency management system, so it does not have the concept of versioning. So we needed some method of being able to update dependencies and make sure that they are compatible with each other. Using Swift Package Manager for the dependency graph resolution means that we would have to write package.swift files for many older dependencies. We could also try to get them merged upstream, which would benefit the Swift Package Manager ecosystem. For more selfish reasons, it would hopefully mean less for us to have to maintain in the long run. So how did that turn out? We were able to successfully remove both CocoaPods and Carthage and have all of our dependencies resolved using Swift Package Manager. However, after a couple of weeks, we ran into some problems. When someone added or removed a dependency, we noticed that Swift Package Manager would ignore the contents of the package.resolve file and try to update all dependencies to their latest version. It turned out that this was a bug. However, we felt it was critical enough for us in CI builds because we didn't want to have to pay the cost of cleaning Swift PM's internal state in between every build. So instead, we've hard-coded the dependency graph in Bazel, and Bazel is fetching all of our dependencies for us. This approach has worked well for us so far, since our dependency graph is fairly shallow. As far as using package.swift to configure each target, that's something that we've pushed back to something to work on later. In the meantime, we manually created Bazel build files for all of our dependencies. But it's something that would lower the barrier to entry for Bazel in iOS projects, so we'd like to see that happen eventually. It seems rather doable at first glance, since Swift Package Manager can dump package information as JSON. However, it doesn't dump information when an implicit setting is used, such as the default location of source code. So those settings would have to be re-implemented. Also, while we didn't plan on doing this at first, we found it was easy to move many of our code generation scripts to Bazel, so we did that as well. This allowed us to both simplify and speed up our build script, since Bazel caches the output just like everything else. So how much of a difference has the caching made so far? If we were to configure Bazel to not use our local cache server, then it will take 10 minutes to build everything. With the cache server enabled, on our office network, Bazel will take around 40 seconds to populate its cache and do any post-processing it needs to do locally. There's still more to our Bazel story. We're still working on improving the developer experience. Right now, any code managed by Bazel is manually pre-built before opening the Xcode project, kind of similar to what Carthage was doing. When developing in Xcode, code managed by Bazel can be viewed and breakpoints can be set, thanks to an open source project called Tulsi. However, we sometimes have problems with code completion results not containing results that should be there. Also, since we're currently pre-building static frameworks outside of Xcode, making modifications to them in Xcode isn't the greatest experience. We do have an escape hatch in our build script that lets a developer bail out of using Bazel and use Xcode instead for specific targets. We also have much more code to add to Bazel. For the most part, the code we're building in Bazel is seldom edited, such as external dependencies, generated code, and utilities. Besides that, we also need to split up our code base more into further refined modules. This will help improve caching and incremental build times between modules in the long run. While we have many modules already, our main app is still the largest build target by far. We also have noticed some issues with Bazel's cache not being usable between machines. Many of these differences, such as different path settings, can be resolved by modifying Bazel's configuration, or just by updating Bazel. If you'd like to hear more about Bazel, don't miss my colleague's short track presentation at 3:30. Thank you.